People are mispronouncing your name. Yes. I'll stay.
Okay. Mentioning pronunciation, this name, the closest I get to the French pronunciation is Broglie. Okay. English, and when I was in college and graduate school, everybody said the Broglie. Okay. Which is kind of the way it looks. But he's French. So. Another thing surprised me. I mean, we studied this guy in the late 60s and early 70s, okay, when I was in school. And in the late 80s, I mean, he's from the generation of Schrodinger and Einstein and all these guys, and we associated him with that. Most of those guys were dead, so we figured he was dead. A guy was a PhD physicist, was teaching at Emory and Henry, and I got to know him and taught some courses for him up there. But we've learned at the same time, the guy was still alive. Then we got to think, okay, he did the stuff in the 20s. In 1990, if he was born in the early part of this century, he'd still be in his 80s. And I think he was. He lived a while. He lived a pretty long life. Okay. Anyhow, talked about the two-slit experiment. Okay. How if you run a wave through two slits, these are the peaks of the wave, and you observe them on a distant screen, you're going to get bright, dim, bright, dim. It'll be bright when the difference in the distance traveled between these two beings is a whole number multiple of wavelengths, in which case the peaks will meet the peaks. And dim when you're a whole number plus half number of wavelengths. And we will observe that in lab. I can't find the handmade diffraction gratings. I know there are roughly 100 of them in here somewhere, but due to the mayhem resulting from the redesign of the building and the disorganization of everything, I don't have time to look through everything to find them. But we'll do something with that because I've ordered some transparencies. It should be here tomorrow, and I'll be able to make the same thing. Okay. So anyhow, that aside, okay, this is light. Now, turns out, should have included slits when I did this. Okay, let's do it again. And of course, the same thing works if you've got a diffraction grating, and you can work out the mathematics of that. You're probably not going to have time, and I'm probably not going to require it. Okay. You have an electron beam. All the electrons move in this direction. Okay. What do you observe? Well, if it's a coherent beam, I think it has to be coherent. I have to think about that. I've never asked myself the question. Electron beam comes in like this. You expect that the electrons that are blocked by the solid parts of the wall, you expect just an image of this thing. You expect bright straight across from here and nothing in between. And straight across from this slit, you expect it to be bright and nothing in between. Over here, the brightness and the dimness would actually be kind of like this. Here it's bright, here it's dim, here it's bright, here it's dim. So it goes from bright to dim, kind of like a sine wave or squared sine wave or something like that, okay? And you can work that out. All you need is high school trigonometry. You know, trigonometry of sums of angles and stuff like that. Just your analytic, I mean, your basic, yeah, trigonometric identities and so forth. Okay, it's not like a bright spot and then a bunch of nothing. Goes from bright to dim if you got two slits. Okay. Now, if you got an electron beam, you would expect something like this because they're electrons. They're particles. They're not waves. Turns out that they are waves. And they're also particles. It turns out that light is a wave. It's also particles, depending how you observe it. And that's brought forth in the introductory problem sets, I think, pretty well. So we'll talk a little bit about how that's done. Okay, well, okay. Really, if you're going to observe electrons, you kind of want to observe them one at a time. Because with a laser, you can get a nice coherent beam. Same wavelength, okay? Everything's got the same wavelength and everything comes in coherent wave fronts, okay? With electrons, it's kind of hard to achieve that. You can do it, but it's technically pretty difficult. So what you do is you've got a cathode, just something when you heat it up, electrons come off of it, okay? And you got an anode, which is like a screen, positively charged, okay? And the electrons go from the cathode to the anode and get accelerated up to, just 50% the speed of light. It just depends on the voltage between here and here, and it doesn't take much voltage, okay? And then you heat up the cathode, but you only heat it up enough that statistically you expect that it's very rare that two electrons would be passing through at the same time. Okay? So electrons pass through these things individually. So an electron passes through here, you expect it to go straight over and hit here. It's a particle. That's what particles do. You shoot bullets, that's what's going to happen. Shoot bullets from way out here in a perpendicular to this thing, you're going to get a bunch of bullet holes here and a bunch of bullet holes here and nothing else. Occasionally one might ricochet off the edge of this thing, but you control for that. So you got to say, no, we're not going to let that happen. Yeah, make a little tube here. Okay. That would work even with electrons. All right. But what happens even if the electrons go through individually is you get this same bright dim type pattern over here. This is not what it looks like. This peak here means that you got a bright spot in this region. Here it means it gets dim. Here it's bright, there it's dim. And I can try to make it look that way. Bright here. It's bright here. It's bright here. It's bright here. It gets less bright as you go down here. It stays kind of, you still got some, pretty much fades out and then it gets a little brighter. I'm not sure you can see that, but it's kind of fuzzy. You can look at two-slit pattern, look up the two-slit experiment with electrons and just look at pictures of the pattern you get. Okay, so electrons are coming through here individually. Now, why do you get the bright dim, bright dim? It's because of interference. Okay. Peaks meet peaks, it gets bright. Peaks meet valleys, it fades out. In between, it's a little it gets fuzzy. Okay. How's that happen with electrons individually passing through? That means each electron is interfering with itself. That means that the electron is essentially a wave in this situation. Okay. Now you can also hit things with electrons, like atoms. And the electrons, in certain situations, act pretty much like particles, but they also act like waves. You have an electron, you think of an electron orbiting a nucleus. That's not really what it is. It's a standing wave. I talked about that a little bit last time. Okay. Standing wave whose wavelength matches the circumference of that hypothesized orbit. And you can look up electron orbitals, the angular momentum, and the principal quantum number, m, as in angular momentum equals nh bar. Okay. It gives you your n equals 1, n equals 2 orbital and stuff like that. N equals 1 orbital is pretty much a spherically symmetric distribution. And n equals 2 orbit, you have a spherically symmetric distribution. But if the angular momentum, at the n equals 2 orbit, you can start against angular momentum, and that distorts the orbit and gives you dumbbell shapes and all kinds of things. You've probably seen pictures of it. Okay. That doesn't mean the electron's really making figure eights. It means you don't know where the heck it is. But the density of that cloud tells you the probability of it being in a given position if you were to try to observe it. Okay. So that's the two slit experiment. And the thing I thought I remembered the wavelength. I mean, the de Broglie wavelength. Okay. But when I did it and worked out the units late last night when I wasn't really too sharp, ready to go to sleep, I couldn't get the units to work out. So let's do the units. Okay. The de Broglie wavelength a particle is lambda equals h over p. P is momentum. Now I tell you that about the fourth, fifth, sixth problems in the introductory problem set. Give you a problem, ask you what's the wavelength of this electron moving at this speed. Assume if I give you the speed and the mass of the electron, you can figure out the momentum. Okay. And if you can't, you look at the solution and it reminds you what momentum is. Okay. And as usual, there's a solution, there's a symbolic solution, there's probably a picture in many of these. And I think the pictures are pretty good. I see things that I want to change in these problem sets. And if I have time, I might figure out how to prompt AI to do that for me. I mean, just things like I say, the uncertainty is this. Well, no, the uncertainty is approximately this. And I didn't use the word approximately. Stuff like that. We'll talk about uncertainty in a minute, but there it is. So if you know the wavelength and you know the separation of the slits, you got a very simple formula for path difference. Okay, set that equal to an integer number of wavelengths. You can tell at what angles the bright spots and dim spots will occur. It's just simple, almost middle school geometry, that. Okay, but the concepts are much above what you get in middle school. But they're concepts that high school students can understand. So it's not deep. So you want to get it into your head well. So if you happen to encounter things like this, you'll not be starting from the ground floor. Okay. Okay. Well, that's the boiling wavelength. So I just complete the picture here. Well, you have single electrons. Again, you just heat up your cathode enough that not too many of them come off. And they're moving at an appreciable fraction of the speed of light. And you get this. Of course, you can adjust the speed by adjusting the voltage and all that stuff. Okay, well, there you have it. Now, I mentioned uncertainty. There are a bunch of formulas that involve H. You know that photon energy is just H times the frequency. Okay. Momentum is energy divided by the speed of light. Little c is the speed of light. You're going to see that. It'll be explained. You want to focus on it. I'm just telling you what to focus on. All the information is there. And then you ought to probably look at text, ask good questions of an AI. Enhance your knowledge a little bit. Learn to do that. Okay? So you have that. Of course, if you know the momentum, energy is 1/2 the square of the momentum divided by the mass. Okay. Momentum's mv. Kinetic energy is 1/2 mv squared, right? So if you square mv, you get m squared v squared. Take half of that and divide by m, you got 1/2 mv squared, right? Okay, so in that kinetic energy, or p squared over 2m, whichever way you want to do it. I'm not sure that enters this discussion an introductory problem set, but it's almost a trivial result of this. Okay. How do you determine the velocity of the electrons in a beam? You run a beam through a magnetic field. Okay. Just a hint, you need to know that. Any charged particle, you run it through a magnetic field. Magnetic field's perpendicular to the velocity, you're going to get a circular path. You do that inside a set of Helmholtz coils, so you got a relatively uniform magnetic field, and you get good measurements. You mess with the system until you got a more uniform field. Is that field, I kind of looked it up because I just don't have the time in the software to do a good job of working it out. It takes software, or it takes the Bessel functions, which I have to bone up on. Okay. You get about a 7% variation between the coils and the Helmholtz coils in the magnetic field. Closer you get to the center, the more stable it is. So if you got a tube this big in the center of 20 centimeter Helmholtz coils, you probably got a magnetic field that doesn't vary by more than a percent or some substantial fraction of a percent. So well, it's in the introductory problem sets. Okay. We talk about an electron and a beam, magnetic field, I expect you to know all that. So you want to be reviewing it. You want to read over them. You want to review them. You want to make notes with things you don't understand. Most of them are fairly trivial, but then every once in a while there's a payoff, and that would be one of them. Well, okay, now, after digressing, okay, these are important relationships. You simply have to know them, be able to use them. So I just read through problems to make myself some notes on topics. Oh yeah, the photoelectric effects. Okay, how do you know that electrons behave like particles? Actually, how do you know that photons behave like particles? You got a chunk of photoelectric metal. You got light shining on it, or electromagnetic radiation of any wavelength. Could be infrared, ultraviolet, whatever. Okay. The light exchanges its energy, which is HF, of course, F is C over lambda. Okay. So like if your wavelength was a nanometer, which would be way below the visible, let's say a wavelength is a micron, which is 10 to the negative 6 meters. Okay. Speed of light's 3 times 10 to the 8th meters per second. Now divide 3 times 10 to the 8th by 10 to the negative 6th, and you get 3 times 10 to the 14th. 100 trillion. Okay. Get into visible light, you get up to 10 to the 15th, a quadrillion cycles per second. Almost too many to count as they go by you. Okay. And they're hard to see in little tiny ways. No, it's not like that. Okay. So you got light. Wavelength, lambda, energy of a photon, hc over lambda. Now you multiply that 10 to the 15th by h, which is in the order 10 to the negative 34th, and you get something in the order of 10 to the negative 19th. 15 from 34 leaves you 19, which ought to remind you of the charge on an electron, 1.6 times 10 to the 19th coulombs, something you should always retain. Okay. One 1.6 times 10 to the 19th joules, for reasons that we saw last time, is an electron volt. Okay. Say electron volts. Now, another thing you do is above this thing, you have a grid. Well, let's give this thing some dimensions. Let's have a grid up here. It's just a bunch of wires, like a screen. And you have some variable voltage. Between here and here. You adjust that voltage so that it repels the electrons that might bounce out of here because of the light hitting them. So what happens? Photon hits electron. Got to be pretty near the surface because the electrons, this metal has resistance. It's a metal, okay? And I'm not sure what the specific metal is or what the specific resistance is. Might be interesting to check that out and share it with us if you find out. Wouldn't take long. Specific metal with some specific resistance, it just means that electrons that aren't near the surface are never going to get out of the surface. Also, the light isn't going to go very far into this. So you're talking about electrons that are pretty much right near the surface, the upper surface of this block. Okay? So an electron hits, the photon hits one of these electrons, giving it 4 electron volts of energy. Maybe. Up to 4 electron volts. Won't be more than 4 electron volts. Okay? Well, that energy will give it, that's going to become a kinetic energy. Okay? And if it escapes the metal without encountering anything else, then you would think that it'd come up, have enough energy to reach this negatively charged 4-volt grid. If you got 4 volts between here and here, you'd expect that it would reach there. But when the electron leaves the metal, it leaves behind unshielded protons, which tend to attract it back. Okay? Does that make sense? I could draw a picture, but I don't want to take the time because we want to get over a lot of stuff, so we can do some other kinds of review. So it takes at least 1.5 electron volts to escape, leaving 2.5 electron volts. And the 2.5 electron volts would be enough to take you up to this grid as long as the potential difference here is not greater than 2.5 volts. Does that make sense? Now, how do you measure that? Well, you are familiar with things that we could use to measure that. Just take a wire here and connect it over here and connect it here to an ammeter. Yeah, and bring the wire down here and connect it to the metal. Okay, or current probe. And then you take this voltage here and you turn up the voltage. Maybe you got a piece of nichrome wire and you got a lead from here to here and a lead from here on the wire to here. One lead goes to the grid, one lead goes to the metal. And you move your lead along that wire to get greater and greater voltage. And you put a voltmeter in there. I'm not gonna complicate the picture, but do you get the idea? You know how to connect those things. You've had your hands on them. You can imagine how to do this. We can't actually do it because it has to be done in a vacuum, and they don't allow us to suck all the air out of the room. It's against state regulations or something. Okay. No, we don't have the tubes. We don't have the high voltage sources and stuff. That you need to do some of the stuff that we do. We do have them, but I despair of training people safely to use them. Okay. It wouldn't kill you, but when you jump back, you might hit your head and something damage it. It's something or your head. Yeah, I don't know which. All right, so there we have it. That's a description. You can read a further description of it if you wish. But what you get is the ability that voltmeter is going to measure something, and that ammeter is going to measure something. Okay? So what you get is the ammeter measures maybe a little less with a little less voltage because you have less current, but all of a sudden, boom, drops off. This would be at the 2.5 volts that would result here. Not particularly difficult to understand. Follow up, understand it. At least look up one description of the photoelectric effect where they show you the setup. Okay? It'll make it more real to you and you'll retain all of this stuff much better and you'll understand it much better. It's an easy apparatus to understand. And look up simplest possible photoelectric apparatus. Pictures of simplest possible photoelectric effect setups because they can get complicated. There are all kinds of things you do to improve your accuracy to make sure that stray resistances don't get in the way and all. And I've never really run that experiment, but and I think I was before I switched to mathematics, I was about to get into labs that would do this, and I mean, those labs can be done in a freshman lab, okay, but they weren't at that point because they didn't fit in. But I never really got to run the thing. Okay. Well, that's the photoelectric effect. And what do we get out of that? We get that light is quantized. The experiment preceded this. Okay. This experiment showed that light consists of little packets of energy. And if you have a single wavelength, you get single packets. And if you change the wavelength, this voltage moves. Okay. Shorter wavelength gives you more energy, so you get higher voltage. So you use, they didn't have lasers, but they had really good diffraction gratings and other stuff maybe that I'm not aware of. Don't have enough imagination to think about it. I haven't seen it. But they had really good diffraction gratings. So you start with a good sodium source or something like that and run it through diffraction grating. And violet's going to be over here and red's going to be over here and everything in between. And you put a little slit here, you get the wavelength you want and shine it on that metal. Okay. It's my stupid interpretation of how it could have been done. Anybody wants to look up how it actually was done? If you find that interesting, it'd be worth doing. And if you do, share it. Okay. And don't feel any pressure to actually do that, but it would enhance your understanding. You've only got so much time in your life to enhance your understanding, so balance it. But try to follow at least a couple of things that are worth following up with your curiosity. Okay. And try to develop the curiosity. I mean, that's kind of key to everything. Okay. Oh heck, I didn't wash that side. Oh yeah, I used that side. It's all right, I got plenty of board left. All right. The uncertainty principle. Okay, let me see. I just want to check and see what the first instance of the first instance of the uncertainty principle occurs there. Yeah, okay. Okay. So you can measure position accurately and I use the word and. Just be careful about the logic. You can measure position accurately or momentum accurately, but not both. Make sure I said it right here. Okay. If delta X and delta P are the uncertainties in position and momentum that you measure, you cannot measure these things to where the product of the uncertainties is not greater than about H. Okay, there's an approximation here. And the reason is not too awfully deep. You have, okay, you got a de Broglie wavelength. Let's say you're trying to measure the position of an electron or proton. Okay, you're trying to measure the position of a baseball. It's got such huge momentum compared to H that there's basically no limit how accurately you could theoretically measure its position. Okay, or if there's a baseball sitting on the, or any of these things, anything sitting on the table. Okay, there's no significant, no observable uncertainty in where it is. If your instruments are accurate enough, you can measure that position very accurately. Okay, I'll say a little more about that. Your momentum is a particle wave. I really can't say what I need to say. The wave nature of the particle gives rise to the uncertainty, and it take a little time to draw that out. So I'm just going to say it's related to the probability waves that are involved here, okay? But we haven't really talked about probability waves. Okay, so if those are your uncertainties, then you got this. Now, you could apply that to an electron orbiting at, say, 10 to the 6 meters per second. That's the order of how fast electrons in the Bohr model would be moving. And you have problems to do that, so I'm not going to do one for you. You need, that's like the fifth problem, okay? That results in an uncertainty in its position. It's about equal to the radius of its orbit. And there's a problem that brings that out, okay? If you do it for a proton in a nucleus, a similar calculation tells you that, well, it's got to be about within the diameter we observe for a nucleus. Okay? After you've done more with those problems, we can say more about it, but that's basically one type of result that gives us really impressive agreement between something that doesn't seem to be related to the radius of the electron orbit or the radius of the nucleus, that kind of tells us what each of those has to be. Not with huge accuracy, but with a pretty good approximation. Fair enough? That's the uncertainty principle. There are other applications, but we'll kind of confine ourselves to the ones right now that you get from the introductory problem set. And the ones that I mentioned are pretty much what you've got. Okay? Electron in an atom, proton in a nucleus. Okay. So relationship between mass and energy. You've all seen this on sweatshirts and places, and something that's kind of culturally common. E equals mc squared. Okay. If m is the mass of an electron, what's E? Well, if m, let's do the mass of a proton or a neutron, and that's around 2,000. Well, that's around 2,000 times the mass of an electron. Mass is around 1.6 times 10 to the negative 27. I'm going back to the electron. We'll do the electron. Now, that's a little more than the mass of an electron. Mass of an electron is about 91.1% of that, but I'm just going to use round numbers because I don't want to get into a whole lot of distraction with the numbers. You work it out with the numbers. 9.11 times 10 to the negative 31st kilograms. Okay, well, speed of light, 3 times 10 to the 8th meters per second. You square that, you're going to get 9 times 10 to the negative 14th joule. And correct me if I'm wrong, but I'm pretty sure that's right. That's approximately 10 to the negative 15th joules. However, the mass is a little bit less than that, so it's a little less than 9 times 10. It's about 8 times 10 to the negative 14th. We'll just say it's on the order of 10 to the negative 15th joules. Okay? And this is approximately equal to 15,000 electron volts. Wait, something's wrong there. I think I went the wrong way with my division. Yeah, that's 6,000 electron volts. And you can check that out. Something you should know already. An electron volt's 1.6 times 10 to the negative 19th joules. It's just the energy of an electron being sucked through a 1 volt potential difference. Okay? And that's just the charge times the voltage. 1 volt times 1.6 times 10 to the negative 19th coulombs gives you 1.6 times 10 to the negative 19th joules. Volt being a joule per coulomb. Okay? Something you should be familiar with. Okay, so if you have 6 of these, then you have 10 to the negative 18th joules, approximately 96% of that. And then 1,000 of those gives you this. So it's actually somewhat more than 6,000 electron volts, but I don't think it goes up to 7,000. Oh, wait a minute, something wrong here. No, it's like 1.67 times 10 to the negative 27th kilograms. This isn't a very approximate value. Introductory problem sets use more exact values. They also are too stupid to round things off at a reasonable level because software was too stupid to do that. Or I was too stupid to take the trouble because it would have been a little bit of trouble with what I had available 30 years ago. Okay. Probably not so much trouble. I shouldn't have gone to the trouble. There it is. Okay, well, that's about 1,800 times the mass of the electron. Okay, be 1,700 times this, but if you use the 9.11, it's more like 1,800. Okay. So that's about 1,800 times m sub e, which means mass of electron. Then E is going to be approximately equal to that can't be right. Should be like 930 million. It's wrong. Something might be wrong in these calculations. if I multiply that by 9 times 10 to the 16th, I get about 1.7 times 10 to the negative 11th, which is off in a lot of ways. Probably remembered something wrong because I haven't really looked at it. Probably should have, but things being what they are. I'll just say you want to check this. This number, which should be close to like 1.67, is kind of like the average mass of a proton or a neutron. There's a difference in the masses. Neutrons are a little more massive than protons. Each is around 1,800, but maybe a little less, times the mass of an electron. Okay? Now, I'm sure of that, at least as sure as I can be. Okay? I've known that always, seems, at least for the last 60 years. Of course, it's been 60 years, so I don't even know what I know, but you get it. All right. It's called an atomic mass unit. You're going to see that AMU in the introductory problem sets. I'm just trying to give you a picture here. You work out the details, okay? Just learn to work these problems and learn to understand them. So an atomic mass unit is about 930 MeVs, 930 million electron volts. So what kind of bonehead error have I made here? Well, work it out and see. Because something's way off here. I mean, that's right. That's the right order of magnitude. It's about the right number. But I'm not getting 930 anythings from these numbers. Okay, so get it right and explain it to me next time, okay? And I'll let you do that. I'm not even going to look it up. The point is that this, Einstein's most famous equation, although it was one of the easiest things he did. Once he had special relativity, it's pretty simple to get this. You don't even need general relativity to do it, okay? General relativity is amazingly difficult, okay? Special relativity is not. We'll do a little special relativity, maybe even today, okay? Just to give you the flavor of it. Just time dilation, bounce a light beam between two mirrors and then get them moving. So we'll probably see that. Okay. I'm trying to think what else you really need to know. The point then is you have atomic nuclei. So I want to talk a little bit about the atomic nucleus. Again, to give you a little perspective. And to relate it to this E equals MC squared thing. For example, let's just consider carbon 12. You can imagine, well, what's 12 mean? 12 is the number of protons in the nucleus. We know that? Is that common knowledge? Because if you've had chemistry, if you use the periodic table and you know that that's how many electrons you got, and the number of protons and number of electrons better be the same, or you got something really dangerous. Okay. And you probably didn't get that deep into the nucleus in a chemistry course, but you should be aware of at least that much of the atomic model and the shell structure and all that, and the S and the P and all that stuff. Okay, which just comes directly from considering the N that we already talked about, the two equations. Angular momentum is quantized, and the centripetal force is equal to the Coulomb attraction. The two equations that kind of form the basis for at least a reasonable understanding of atomic theory. You throw angular momentum into that, and you get some changes in energy levels and stuff. And also, you got the Pauli exclusion principle. No two particles can occupy the same quantum state. And that gives you the whole shell structure and valence and all that. In chemistry, it all comes from atomic, just from Coulomb's law, quantization of angular momentum. And that's about it. You also got the magnetic quantum number that makes little differences. And then electron spin. Electrons don't really spin, but spin measures the quality of electrons that makes them act a little differently in a magnetic field depending on the spin. Okay? That's the physics. Chemistry doesn't go much beyond that. They just work out a lot of details that physics doesn't bother with. Okay? Ultimately, it's all physics, but there. Okay, you got carbon 12. 12 protons within a diameter about 10 to the negative 15th meters, might be 10 to the negative 14th. I haven't measured one lately. Okay. How much force would one proton exert on another at 10 to the negative 15th meters? Let's say 10 to the negative 14th meters, because we don't want to overstate it. Okay. And it could be confusing diameter of the nucleus with the observed diameter of a proton, which has kind of been observed. Okay. Force and repulsion, two protons separated by 10 to the negative 14th meters is F equals K times the square of the charge on a proton divided by the square of square. K, Q1, Q2, Q1 and Q2 are equal over R. Okay? K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. So that's about 10 to the 10th, isn't it? You square 10 to the negative 14th, you get 10 to the negative 28th, which brings us up to 10 to the 38th between the denominator and the numerator. So far I got like 10 to the negative 38th newtons per squared Coulomb. Okay. But you square a Coulomb and you get about 10 to the negative 38th. Okay. And what you get here is approximately 2 newtons. It's like half a pound. That's a force between two of these protons confined in this small area. Okay? What in the world is going to hold them together? Well, if you've got just 2 protons that close together, throw in 2 neutrons. That gives you a helium nucleus, which is an alpha particle. I left the U out of neutrons. Now it looks even worse. But that's what it is. It's 2 neutrons. Protons and neutrons exert a force on one another. It's only significant over short range, like 10 to the negative 13th, 10 to the negative 14th, 10 to the negative 15th meters, okay? It's a short range force. It drops off very rapidly. Acting strong force over short distances. Become the electrostatic repulsion to the protons if you've got enough neutrons. One neutron isn't enough to keep 2 protons confined to a nucleus. They would fly apart quicker than you could blink your eye if you were a proton. Okay? Protons have very quick eyes. Okay. 2 neutrons is enough, and helium nuclei are very stable. Okay? Three neutrons work all right. If you get too many neutrons, you can kind of think of it as they start getting too far away from each other and they don't hang together. So you can't have too many neutrons. You got to have just the right number. Sometimes there is some wiggle room in the number of neutrons you could have. Like carbon 12, okay, has equal number of protons and neutrons. Carbon 14 has a couple of extra neutrons. and it decays. It's what you use to do radioactive decay. It decays slowly, takes 14,000 years or something like that for it to decay down to half, but it decays. Okay, so that's just, very vague, very unspecific overview of the whole idea. Uranium has 92 protons. Uranium-238, well, subtract 92 from 238, and you get 140 neutrons. So you get almost half, again, as many neutrons as protons to hold uranium nucleus together. You go beyond uranium and it doesn't occur naturally, but you've got a whole series of more than a dozen heavier elements that have been synthesized. Okay? You just start shooting protons and neutrons at each other and whatever, shoot neutrons at nuclei and see if some of them stay stable for a nanosecond or a nanopicosecond or whatever. But they all decay rather quickly. Some surprisingly not as quickly as others, but they all decay really quickly. So that's a little bit about an atomic nucleus. Now, when an atomic nucleus decays, that means that uranium is radioactive, right? Okay. There are three ways an atomic nucleus can decay. The nucleus can emit an alpha particle, which is 2 protons and 2 neutrons. Okay. And if you're near a nuclear event, alpha particles are the ones you really don't want to inhale. Okay. They'll cause cancer wherever they end up in your body. So if you see one coming, get out of its way. Okay. When you emit an alpha particle, I'm not going to say this, it's all written down there. You lose 2 protons and 2 neutrons, which means your atomic number goes down by 2. Your atomic mass goes down by about 4 atomic units, four atomic mass units. Okay. And all that is stated pretty explicitly in the introductory problem sets. So you got one element that emits an alpha particle. And maybe any atom has a 50-50 chance of emitting an alpha particle in 3 billion years. So it decays rather slowly. It takes 3 billion years to get down to half of the activity that you used to have. Okay. Some decay very quickly with a half-life in seconds. Okay. Or nanopicoseconds if you use synthesized stuff. Okay. It's around the time it takes a light beam to cross a helium nucleus. Okay. And I could be wrong about that. I haven't figured it out, but it's something like that. And it's something you can easily work out. Okay, so you can emit an alpha particle. When you emit the alpha particle, the total mass of the alpha particle and the remaining nucleus decreases. The remaining particles, which is which are the alpha particle and the nucleus, then fly apart with a kinetic energy that's equal to 1/2 delta M C squared. So I'll say that the kinetic energy increases by 1/2 delta M C squared. The delta M is called the mass deficit. Okay. And once you know what the mass deficit is, it's really easy to calculate the kinetic energy. And if all the energy is in the alpha particle, which it pretty much is if you have a massive nucleus, it's just like, well, the ratio of the velocity is basically equal to the ratio of the masses when a particle decays. And if the ratio is like 20 to 1, then the recoil velocity ratio will be like 20 squared to 1, 400 to 1. So if the uranium nucleus emits an alpha particle, 399 out of 400 parts of the kinetic energy of the velocity, no, the kinetic energy are in the alpha particle as opposed to the uranium nucleus. So that might not be exactly correct, might not have said it exactly correctly, but that's the idea. In the introductory problem set problems, when I ask you a problem of this nature, I say assume that the remaining nucleus doesn't carry off any important kinetic energy, that all the kinetic energy carried off is in the alpha particle. Okay. For government work, that's close enough. They'll still kill people. Okay. They'll still create a nuclear chain reaction if that's what you're trying to do, which you don't really want to do. Okay. Make sense? That's not difficult to understand if you understand momentum conservation and energy conservation and accept the E equals MC squared. Okay. You have another mode. Beta decay. Where neutron emits an electron. Now, neutrons don't have electrons in them, but to say the neutron emits a proton would be more proper to say a neutron undergoes a quantum reaction, quantum event, becomes a proton, and an electron carries off a little bit of the energy because, again, you get a mass defect, which I'm not going to write down here. If you understand that total mass here decreases, total mass here also decreases. Okay. And then a gamma decay. And incidentally, the beta decay increases the atomic number because a neutron changes to a proton. That means you got more protons, it means your atomic number goes up, right? Okay, and gamma decay, it's a change in energy levels in the nucleus. That's the easiest way to understand it. And I don't understand it a whole lot better than that. Okay? Because working out the quantum mechanics of the nucleus took a lot of really great minds, a lot of time to get anywhere with it. Okay? So I don't touch it. There are a lot of things I'd like to learn that my curiosity would lead me to, I'd forget them quick, but it'd be nice to learn. But that's one I'm not going to touch. Okay. And most of this I'm not going to touch. Nuclear physics is tough stuff. Okay. When you really get into it, changing energy levels in a nucleus. The energy loss is carried off by a gamma particle. That's nothing but a very high frequency photon. And gamma radiation is very penetrating. X-rays go right through you because they're high frequency. Gamma rays are way higher than X-rays. Okay. Because they come from nuclear interaction, they'll typically have a lot of it. If you some means they have very high frequency. Now you can look up more about those different particles and their effects on tissues and stuff. But that's just kind of an overview of the different decays. Problems that I ask generally say, you have this much mass deficit, you have this, where does the energy go? And the answer is usually pretty simple if you understand what I just said. And in addition, understand it as this explained in the problem sets. Fair enough? Okay, now that's a whole lot of it. I did get to relativity today, so you got that to look forward to next week. Might even talk about it a little bit in lab just to get you started on it. So we'll have lab Friday. We'll try to observe effects of RC, LRL, and LRC circuits using the function generator. And I think we're going to be successful with that. And we'll do, we don't do an actual two slit or multi-slit experiment. We'll do a one slit experiment with a slit of varying width and get some ideas out of that. That one's a little harder to understand, but it's not terrible. So there we are. Get these problem sets down, review all the problem sets and everything we've done in lab, and start reviewing it now, if only by spend 15 minutes a day looking back over it. Try to form wholes, okay? Whole bits of understanding that ties things together. All right? Okay, well, good luck with it, and I will see you Friday. Got any questions? Stick around.